Hello, my name's Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering at the University of Calgary. And in this lecture, we're going to talk a little bit about programming languages. To start out with, I want to talk a little bit about how a microarchitecture runs a program. And a microarchitecture runs a series of very low-level instructions or commands called machine language commands. And basically, if you look at sort of the logic design at how a microarchitecture works, it basically reads one of these low-level machine language instructions out of memory, feeds it into the processor, and executes it. Then it reads the very next one out of memory, and then it feeds it to the processor, which executes it. Then it reads the very next one out of memory, and then it executes it, and so on and so on and so on. So basically, all a microarchitecture is doing is reading and executing. And so one of the things that I'm going to try and address in this module is how does a high-level program written in, let's say, C or Python get translated down to this very sort of simple abstraction for running or executing a program. So in this module, I'm going to be talking about something I'm going to refer to as the big three. And the big three different kinds of programming languages are high-level programming languages, machine language, and assembly language. And so to start out with, high-level languages are things like C, Python, the kinds of languages that you're probably already familiar with using from a programming perspective. Machine language, on the other hand, are the actual binary commands that we feed directly into the processor's digital logic structure. So these are the ones and zeros, the digital voltage levels that literally get fed into the circuitry that makes up our processor. And these are very, very low-level commands. The third type of language is something that we're going to refer to as assembly language, or something that is referred to as assembly language. And you can think of assembly language as an intermediate language that humans can read, but is very, very tightly tied or very, very closely related to machine language. There's almost, but not quite, a one-to-one mapping between assembly language instructions and machine language instructions. And again, this is maybe something that we take for granted today, but it's worthwhile pausing here and to just appreciate what a significant innovation human-readable programming languages were. So back in the very early form of computers, back when people were using the very first generation of computers, humans had to actually by hand encode the ones and zeros that made up the machine language instructions that were fed into the processor. This is basically what punch cards were, if you've heard of punch cards. And so the idea of having a programming language that humans could read, that we could type in using alphanumeric characters, was a big innovation. And actually, assembly language was the first form of human readable programming language. And as you're going to see, because we're going to talk a lot about assembly language in this class, as you're going to see, assembly language, while you can get the hang of it, it isn't quite as intuitive as, for example, a Python program. So as soon as people started to work with human readable languages, the race was on to develop languages that were more and more intuitive for humans, but at the same time were mappable down into the low-level machine language instructions that processors needed in order to take action on something. So starting off with high-level languages, again, these are the languages that probably you are most familiar with at this point, and they include basically almost every programming language you can possibly name. C++, C, Perl, Python, Ruby, MATLAB, awk, JavaScript, Java. All of these things are considered high-level programming languages. In this series, or in this class, we are going to be using primarily C. And there's two reasons for that. The first reason is that C in general is relatively, of all the high-level programming languages, it's probably the easiest to map to assembly language and machine language. And so I'll be using that in a lot of my examples. And it's also the primary language we're going to be using in our hands-on work with our microcontrollers when we start to implement designs using microcontrollers. Now, many, not all, as we're going to see, but many high-level languages are translated into machine language using something called a toolchain. And a toolchain is basically a series of specialized programs that convert a high-level language down to the low-level machine language instructions that can be fed directly into a processor. And we usually refer to this conversion as compiling a program. So when we compile a program, we take a C program, for example, and we compile it down to an executable file or a binary file that contains the actual ones and zeros of the machine language instructions that can be fed into the processor. As we're going to see, compiling is, even though that's the term that we use, compiling actually refers to just one specific part of this conversion process, and we're going to see that in a second. However, it's worthwhile just at this point pausing for a second and talking about interpreted high-level languages, because many of the languages that you may already have experience with are not actually compiled languages, they're interpreted languages. And probably the most common example of that these days is Python. So you don't actually compile a Python program. Instead, you write a Python script. We refer to generally Python programs as Python scripts. And then that program gets read by an interpreter program. And the Python interpreter basically reads the scripts and then sends commands to the processor based on what's written in those scripts. So the interpreter is a compiled program. So somebody had to program the interpreter and compile it. But when you actually execute your Python script, you're not actually doing any compiling. And that's why maybe if you have programming, you may have a lot of programming experience, but you have never actually compiled anything before. And we're gonna, as I said, we're gonna focus on C in this class. So we're gonna be dealing with a language that is compiled. And so we're gonna be talking about the tool chain and how that process of conversion to machine language works. So as I mentioned, assembly language was the original human readable language. And there is an almost but not quite one-to-one mapping between an assembly language instruction and a machine language instruction. As we get into assembly language, you're going to see why I make that distinction. And there was a time when humans would write assembly language programs from scratch. And the original reason for this was back in the day, it was relatively common for humans to be able to write more efficient assembly language than could be generated automatically by a tool chain. However, these days that's not really true anymore. Most modern tool chains are pretty good at generating highly optimized assembly language, and so you don't really get much of a speed up advantage when a human tries to write assembly language from scratch. However, if I talk to my friends who work in firmware and embedded design, they say that they do work with assembly language quite a bit still. Not so much to write assembly language, but to look at it to understand why a processor is behaving the way that it is. And this is relatively common for very high speed, quote unquote, real-time applications. So imagine if you're writing a processor to control a self-driving car, or maybe even a drone or a fighter jet. That processor has to be able to receive input, make a decision, and take action quickly enough to, not crash the car or fly into the side of a mountain if you're piloting a drone. And sometimes with these very time-critical applications, the processor may end up taking a little longer than you expect. And it's nice to be able to sort of look at the assembly language and sort of see the exact instructions, kind of figure out what's happening, and then see if you can change or optimize the program to reduce bottlenecks. Another reason, and really the primary reason why we study assembly language, is that it is absolutely, it must be understood by the designers of tool chains and microarchitectures. It is impossible for you to understand the hardware design of a computer processor or a microarchitecture without also understanding assembly language. That's fundamental. You need to understand these low-level commands that are being executed by your microarchitecture. And if you're ever fortunate enough to work in a job where you're developing a new processor, a new GPU, a new ARM core processor or something like that, then how you design your digital hardware to support your machine language instruction set goes hand in hand. And you may choose to make certain choices when developing your instruction set that will have certain implications on how simple or complex the hardware is to actually support that instruction set. And hopefully that will become clear as we work through this class, because as I said, we're going to get right down to the digital logic level when we start to build up our microarchitecture, but hand in hand, step by step, we're going to also be talking about assembly language and machine language as we develop the hardware. So we're going to be simultaneously talking about hardware and software all the way through this course. So when we talk about machine language, machine language commands are the binary instructions read from memory and dumped directly to the processor for execution. And so these are very, very low level commands. And, as we talked a little bit about in the introduction, the family of machine language commands that can run on a microarchitecture in many ways defines the architecture itself. And so the digital design of the microarchitecture, like the actual digital hardware blocks, will be developed simultaneously with the notion of what kind of instructions we want to run on those digital blocks. And there are basically, when we look at architectures from the machine language perspective, we can divide architectures into two very broad categories: complex instruction set computers, or CISC computers, and reduced instruction set computers, or RISC computers. So RISC architectures tend to use fixed length machine language instructions. And the architectures that we're going to be talking about in this class, ARM and the AVR architecture, are both RISC architectures. So ARM processors use 32-bit instructions, and the AVR architecture mostly uses 16-bit instructions, but sometimes for very complicated commands we'll also use 32-bit instructions. But most of what we're going to be talking about in this class will focus on the 16-bit instructions. CISC machine language instructions are variable length, and the most common example of CISC architectures are the Intel x86 architectures. A machine language command contains two types of information. The first is a field, sometimes called the funct field, but usually called the opcode field, that specifies the type of instruction being executed. So the opcode will say this is a multiply instruction, or this is a load memory instruction, or this is a store memory instruction. So these opcodes are basically labels that indicate what kind of instruction the processor needs to execute. And in addition to the opcode, typically the machine language instruction contains arguments or the operands of the instruction. So for example, if we're adding two numbers together, the opcode would say this is an add command, and then the operand part of the machine language instruction would tell us exactly which two numbers we're adding together and where we should put the result. Machine language commands are ultimately placed in some kind of executable file. And so when you create an executable file, when you compile a program, the executable file is a binary file, and it literally contains a whole bunch of machine language instructions, one after the other. Okay, so I want to conclude this module or finish it up by looking a little bit more closely at the toolchain. And the operation of a toolchain can actually be divided into 4 different stages: the preprocessor, the compiler, the assembler, and the linker. So you'll see that, while we usually use the word compiling to refer to the complete process of taking a high-level language and creating an executable file, it actually refers to just a very specific portion of that process. So the first thing I want to talk about is a preprocessor. Now, a preprocessor doesn't necessarily exist in all tool chains, but it is something that does exist in C and C++. And it basically converts C code to C code, which is a little bit confusing, but I'll show you an example. And the reason why a preprocessor exists is to basically allow a more efficient programming style without sacrificing, without bringing in a lot of overhead. And so, for example, you can make things that kind of look like functions, but aren't full function calls, and they tend to perform a little bit better or a little bit faster than actual function calls. And the output of a preprocessor is a translation unit. And so there's a bunch of different functionality in the preprocessor. So if you've worked with C or C++ macros, for example, that's a structure made possible by the preprocessor. But most people are most familiar with using the preprocessor to define constants and to include header files into different C or C++ source files. And so basically, whenever you see a hashtag in front of a command in a C or C++ file, that's a preprocessor command. And so all commands that start with hashtags are interpreted by the preprocessor. And so we start with a C or C++ source file, and then we translate. The preprocessor creates something called a translation unit. And so, for example, we can use the capital word const to represent 33. And then, we can, if we have an argument here, we can add const to it. And by giving it a name rather than just a value of 33, that helps make our program more readable. But the preprocessor will we'll look for all occurrences of the keyword const and substitute in the value 33. So when we look at the translation unit, the keyword const is gone and it's been replaced by 33. Also, if we have, in our header file, if we have any function declarations, those are, in this case, the function declaration is removed and the full source code definition of the function is placed in the start of the C file. And so it's a subtlety. It only exists for C and C++. It translates C to C. So we haven't really even started along the journey to creating our machine code just yet. But it is an important part of C and C++ tool chains. So the next stage is the compiler, and the purpose of the compiler is to convert our high-level language, in our case our C, into assembly language that is written to an assembly language file. Now, for those of you who have compiled C and C++ programs before, you probably don't remember having assembly language files just kind of lying around in your development directory. And that's because they are intermediate, and even though assembly language is generated, it's immediately deleted by default by most compilers these days. You have to sort of enable certain options in your compiler so in order for the assembly language to hang around. And so here's an example. The compiler operates on our translation unit, so this is our C code, and it converts our C code into assembly language. And this is a MIPS assembly language implementation of that C translation unit. And don't worry about understanding what all these commands are just yet. We are going to get into this in a lot of detail as the course progresses. Now, the assembler then is responsible for taking the assembly language produced by the compiler and translating it into the actual machine language instructions that will run on the processor. And the output of an assembler is stored in an object, what's known as an object file. And so an object file is a binary file that literally contains a whole bunch of binary machine language instructions. And an object file can be divided into kind of three parts. There's what's known as the text segment, which contains the machine language instructions of the program. There's also something called a data segment that is used to initialize variables that are stored in memory on the microarchitecture. And then there's a third area that contains a bunch of information that helps with linking. And as a segue into that, linking is the final stage of the tool chain, and it is what makes it possible to use programming libraries. Now, reusing other people's code is fundamental to programming efficiency. We've all written programs where we've, for example, used printf to print to the screen, or we've used functions to take input in from the keyboard, or generate a little bit of graphics on the screen. And to do all of that, we use pre-written functions that are stored in something called libraries. And without libraries, programming would be incredibly inefficient, because every time anybody wanted to do anything, they would have to write all of their stuff from scratch. And so we make use of lots of standard functions, as I said, printing, as simple as printing out to the screen with printf, and as complex as using GPU accelerated machine learning algorithms. And so part of my research is machine learning, and I use pre-written machine learning functions all the time. I don't, rewrite all of the machine learning algorithms that we use for our work. And the machine code for all of these pre-written routines are stored in special files called libraries. And the purpose of the linker, the final stage in our tool chain, is to basically take the object file that contains the machine language of the code that we've written and connect it to machine language instructions that exist in libraries in order to produce our final executable file that can actually run as a completely atomic program on our processor. And the result is stored in, sometimes we refer to these as executable files, sometimes we refer to them as binary files. And so again, the linker sort of takes our object file and then pulls object code out of libraries depending on what pre-written functions we want to use in our code. So this notion of taking machine language code from our executable and connecting it with machine language code from a library is referred to as linking. And linking can actually be done in two different ways. We can use what's known as static linking, and we can also use what's known as dynamic linking. And so first of all, static linking is where all machine language code from a particular library is copied over into the executable. This is the type of linking that's done for very simple microcontrollers. So for example, when we program the AVR chip for the hands-on exercises in this class, our tool chain will always use static linking. So if we use a library function, for example, if we take the square root of something and we use the square root function, that the machine language code for implementing the square root will be copied into our executable. It's basically, or what we would often refer to as a hex file when using this particular tool chain. And then that executable, or that hex file, is completely copied over or loaded into the AVR chip. So the advantages of static linking: it's easy to understand, it's easy to port software between machines because everything you need, all of the machine language instructions are contained in your executable. The disadvantage is that you can create very big executables. There's really no way to avoid this when you're doing firmware development for embedded devices, like programming our little microcontroller. But it does sometimes come as a surprise, like if we use a whole bunch of library functions, we might compile and then find out that our program doesn't fit on the flash memory in our device, and it's because we've used so many libraries. In contrast, dynamic linking doesn't copy in all the machine language code from the libraries. Instead, it only copies in the locations of the libraries. And the operating system then is responsible for connecting our executable to those libraries in real time. And so the executable will start to run, and when it hits a library function, the operating system actually connects our program to the machine language in the library in real time and allows our program to execute that code. This only works for devices that have operating systems, and so we won't be using dynamic linking in our hands-on exercises for this course, but it's just important to know that it exists. The advantages of dynamic linking, I think, are kind of obvious. Smaller executables, since we're not copying in all of that code, allows programs to take advantage of library upgrades. So for example, if some improvements were made to a library function, our executable can then jump to the upgraded library and hopefully run in exactly the same way. This is more efficient for multitasking operating systems as well. But the disadvantage is it's harder to understand and can cause some software installation problems if you're trying to run a program on a computer that doesn't necessarily have all of the required libraries.